Hello everyone. In today's class, we will discuss one of the application of definite integrals. We are computing work done by a force. So let me start the class right away. First, quick recall. Force equals to mass times accelerations, and the unit of force is Newton. We denote by N, which is kg times meter per second square. The work for a constant force, work equals to force times distance, and the unit for work is joule. For the variable force Fx as a function of distance x that moves an object from x equals to a to x equals to b is denoted by W and is defined by the definite integrals. So W equals to definite integrals of force from a to b. Great. So another definition is the Hooke's law. The force required to maintain a spring stretched x units beyond its natural length is proportional to the distance x. So that is Fx equals to k times x, where k is a spring constant. So here, this is the natural length of the spring, the top curve here. The bottom curve here is a stretch. The same spring up to this length is a natural length, and we force it to stretch this x units beyond its natural length. So we use the force. That force is constant times the distance. That's according to Hooke's law. Awesome. Now this section is very short and sweet section, so let's do example. First example. Example 1. How much work is done in lifting a 15-pound rock to a height of 7 feet? So here force is constant, so our work done is force times the distance. So F times D, so 15 times 7, 105 foot-pound. Great. Example 2. When an object is located at a distance x feet from the origin, a variable force, which is given here, x squared plus 2x, acts on it. How much work is done in moving the object from x equals to 1 to x equals to 3? So to compute the work, I need to use the definite integrals of the variable force. So work done equals to definite integrals of the Fx. Fx is x squared plus 2x from 1 to 3. Then let's take the integral. The integration of x squared becomes x cubed over 3 plus integration of 2x becomes 2x squared over 2. 2 cancels, so simply x squared, and evaluate at x equals to 1 to 3. I hope this makes sense to you all. Then after simplifications, after plugging those values, we will get 15/3 foot-pound. Awesome. Let's move on. Then another example 3. A force of 10 pounds is required to hold a spring stretched 4 inches beyond its natural length. How much work is done in stretching the spring from its natural length to 6 inches beyond its natural length? So first let's find the spring constant using the Hooke's law. Then our Fx equals to k times the x, and then take the definite integrals. So here is our unit is pound here and inch here. So I need to convert this inch to feet. So I need to divide by 12. So 4 inch is same as 4 over 12 feet, which is 1/3 inch. Similarly, convert 6 inch to feet, 1/2 feet. Okay, great. Let's begin the solution. So by Hooke's law, 10 equals to k times 4. 4 is 1/3 feet, so k times 1/3. Multiply both sides by 3, so k equals to 30. So now we found the spring constant. Then according to Hooke's law, our force equals to 30 times x. Great. So next, to find the work, I need to take a definite integrals. So thus the work done in stretching the spring from its natural length to 6 inches, same as 1/2 feet, beyond its natural length is, for the definite integrals of the force. So here x equal to 0 corresponds to the distance from the natural length of the spring. That means no stretching. And then we stretch 6 inches, which is 1/2 feet. So this is 0 to 1/2, the force. Fx equals to 30x. Definite integral 0 to 1/2. The integration of 30x is 15x square. 30x square over 2. 2 cancel 30 15 times. So I just skip there. 0 to 1/2. And just put x equals to 1/2. X equals to 0. Simplify. It gives you 15/4 foot-pound. Great. So we finish these sections. Thank you.